Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to learn how to isolate the behavior of individual variables in a model that has multiple continuous variables. If you remember from the discrete case, we call the distribution of individual variables in a model that has many variables the marginal distribution of those variables. Today we're going to learn how to derive the marginal distribution of continuous random variables. Our motivation is that if we have a model with many variables, how do we characterize the behavior of individual variables? For example, here we have this cartoon example that we've been using where the density is constant in this triangle. Remember that the triangle represents a lake where there's an otter that is swimming in the lake and we don't know where it is. We model its location as having constant density within this triangular lake. And now we're going to imagine that we only care about the position, the y coordinate of the otter. We couldn't care less about the horizontal coordinate. So how do we characterize the vertical position of the otter? Essentially what we want is the PDF or the CDF, but usually we use densities. So the PDF of the random variable that represents the y coordinate, which we call a with a squiggly line because it's a random variable. All right, so how do we go about that? In general, when we want to characterize the distribution of a single random variable, we start with the CDF. Even if what we want is the PDF at the end of the day, we can always obtain the PDF by differentiating. Why do we use the CDF? Because it has a really intuitive definition in terms of probability. It's the probability that the random variable is more or equal to any fixed value. Okay, remember that here A doesn't have a squiggly line, that A doesn't have a squiggly line, so it's a fixed value. So what is that probability in terms of the information that we know for our problem? In our problem, we know the joint PDF of the two coordinates, right? We know that it's constant within this triangle. And we can use that to compute that probability. How do we do that? Well, we integrate over the appropriate set. So what are the set of values of A and B such that the coordinate that we're interested in is smaller than that fixed value? Well, we have to integrate the first coordinate, the vertical coordinate, from -infinity to A, right? And then we have to integrate the other over all of its possible values because we don't have constraints on the other coordinate. Okay, so hopefully this makes sense. All we're doing is we're applying this property of the joint PDF, which is that you can compute the probability that the 2D random vector is in any set by integrating over that set. All right, but now what if we want the PDF of A? Well, what do we need to do? We need to differentiate. And now this might be a little bit tricky, might seem a little bit weird because we have this integral here. So you might have some trouble, but you just have to imagine this whole thing as a function of A, which it is, right? Because if we change A, this changes. And B is going to be, we're going to integrate it out. So once we take this integral, there's not going to be any dependence with B anymore, right? So now, what is the derivative of this quantity with respect to A? Again, now you're going to have to, because of the presence of the integral, this might look a little bit confusing. You need to think about this as if it looked like this. An integral from -infinity to A of some function g of u du, which it is, right? If g of u, if we set g of u to equal this part. Okay, so this part would be g of u. It is a function of u, right? So if you remember, by basic calculus, the derivative of a function of this form, excuse me, is just g of A. Okay? So if g of u is all of this blue stuff, when we take the derivative, what are we going to obtain? The integral over B of the joint PDF. Okay, so again, this is just from the properties of the joint PDF and basic calculus. what we find out is something very intuitive, which is if we want the density with respect to A, we have to integrate out the other variable. So we integrate with respect to B. This is exactly the same as what we did in the case of discrete random variables with the joint PMF, except there we would sum over the other variable. Here we have densities, so we integrate over the other variable. Let's take a look at our example again. So now the idea is that if we want to know the density at a certain point, let's say here at 0.5, what we're going to do is we're going to integrate the 2D joint PDF over that line. And when we integrate over that line, that's going to give us the 1D density at this point. This is what we derived. And again, it's a direct generalization to the continuous case of our discrete result where we were summing the joint PMF over one variable to obtain the marginal PMF. When we do this, we call this the marginal density of the random variable. So let's do this. So here we would integrate, for example, here from 0. Okay, so let's see. I just want to make sure that my line is straight. Okay, we would integrate from 0 to this point here. What is this point here? Well, it depends, right? It depends on the value of A. In general, that point is going to be 1 minus A. Okay, the values where B are non-zero go from 0 to 1 minus A as long as A is between 0 and 1. So when we perform this integral, this is why we're going to be integrating from 0 to 1 minus A. And remember that the density is not equal to 1 because the triangle has area 1/2. So it has to integrate to 1. So the density is actually 2. All right. So when we put everything together, we see here that the marginal PDF of the random variable A that models the vertical coordinate is equal to 2 times 1 minus A, which basically it looks like that, which makes a lot of sense because just visually you see that there's a higher chance that the other is around there than here, right? And it's diminishing. This is captured by the marginal PDF. In general, we define the marginal PDF based on the formula that we have derived as the integral of the joint PDF over the variable that you don't care about. What if you have D variables and you want to isolate the behavior of just one of them? So here we're putting the D variables within a random vector of dimension D. Remember that that's completely equivalent. You can talk about multiple random variables or coordinates of a random vector. It doesn't matter. So what are we going to do to isolate the behavior of the ith entry of the random vector? We're going to integrate over all of the other entries. So realize that here we're not integrating over the ith entry, we're integrating over everything else. All right? The ith entry here is fixed to equal A. Okay, and then we're integrating over all the rest. What if we want the joint PDF of a subset of the variables in a model? In that case, we have to integrate over the rest by the same argument that we used to derive the formula for the marginal PDF in the case of two random variables. So here, if we're interested in the joint PDF of x1 and x4, we need to integrate. So this is going to be a 4-dimensional random vector. We integrate over the second and the third entry. All right, you see that here. We integrate over the second and third entry. And here I should have written that this goes, you have to integrate from -infinity to infinity. Had forgotten the upper limit. There are always typos. It's quite maddening actually. Like I've been using these slides for years and typos always manage to appear somehow. All right, so hopefully that's clear. Now we're going to look at some real data. Here we have the joint distribution of the temperature in Versailles and Manhattan over a year. This is Versailles, Kentucky and Manhattan, Kansas. we can compute we can estimate the joint PDF applying multidimensional kernel density estimation, as we explained in the previous video. Now we can ask ourselves, what if we want to know the marginal PDF of the temperature in Manhattan? How can we obtain it? Well, we can just integrate over Versailles. Okay, if you integrate over Versailles like that, you're going to get this distribution. Now imagine that you want the... wait, no, I did it completely the opposite way. Of course, I did the opposite way. So let me redo that. Hopefully you noticed, you see that this is Versailles and this is Manhattan. So if you want this density, you have to integrate this way. Okay. You have to integrate that way. And then you get the marginal of Manhattan. What happens if you integrate horizontally? You get the marginal of Versailles. Now, let me ask you a question. Is this how you would compute the marginal PDFs in practice? Would you do multidimensional kernel density estimation and then you would integrate somehow numerically on your computer? Think about it. You can pause the video if you want. The answer is no. The answer is, what would you do? You would just take all the temperatures in Manhattan and you would apply one-dimensional kernel density estimation to those, and then you would get this PDF. Or you would do the same for Versailles and you would get that. Because you have to remember what the marginal PDF actually means. It's the behavior of that particular variable. So if you just have the data for that variable, you can compute its density directly. Hopefully that makes sense. And you're going to obtain a very similar result. What have we learned? We have learned the definition of marginal distribution. We have learned how to compute it from the joint PDF. And we have seen some examples with real data. And that's all I got. Thank you very much.